Hello, welcome back to day 2 of Raising Climate Ambitions with Biochar. I'm Daniel with the virtual event team, We and Goliath. And like yesterday, I'm going to just give you a quick walkthrough of the event site, let you know anything you need to know. If you weren't here yesterday, this is how to navigate. If you were, here's a quick reminder and maybe a couple new tips. The agenda is where you'll find the full schedule. So it'll auto take you to today, but if you want to explore other days, just use these tabs here. Like you already just did, you're going to click join session to come into each session. You will need to switch links between each session, okay? So when you're done with one session, you'll probably see links pop up right there where the video is playing now. But if you don't, just click agenda, scroll down and click join session for whichever session's next. At the end of each day, we have virtual networking, and that's where you can go to the lounge, rooms, people, and exhibitors, and connect with other attendees, sponsors, and even speakers. Okay, so you can see all of the wonderful exhibitors here with their booths. Go ahead and click into booths to explore their services, offerings, people, and you can start a chat or send a one-on-one meeting request with anybody. Feel free to keep multiple chats going on by hiding them like that as you explore the site. In the lounge, we have some open networking and fun areas to hang out. In the rooms, we have themed discussion based on each session of the event, as well as to discuss with our sponsors. So you can learn more about their offerings. Come here for tech support help if you need. And on the People tab, this is where you find the full list of attendees and speakers. So you can reach out to anybody and start a conversation, okay? On the right, in addition to the chat for sessions, you'll find an event-wide feed. So feel free to use this to ask any open questions to everybody, introduce yourself with audio post, share images, even ask a poll-based question. And you can always see what's happening now right here. And you can see who's at the top of the leaderboard. And as a last note for the day, I want to just mention we have some fun prizes from IBI, as you'll see on the homepage here. So our top most engaged attendees will win a copy of the Burn book by Kathleen of IBI, a biochar shirt or magnet. So enjoy day 2. Have a great time. And over to you, Kathleen.
Thank you, Daniel. And welcome back, everyone. We hope you learned a few new things and met more than a few new biochar friends yesterday. As I mentioned in my opening remarks, we appreciate your patience in learning with us how to optimize your experience here on the Hubaloo platform. One thing we learned yesterday is that lounges are a bit like speed dating events where you have a limited time to get to know your fellow loungees, whereas rooms are more like a small dinner party that allows for longer conversations, but with fewer attendees. So in light of that learning, as Daniel mentioned, we are expanding our use of rooms today so that extended conversations can be supported. So we're setting up rooms for our top level sponsors and for the panelists for today. And we hope that at least a few of today's speakers could stay for the networking period to answer any additional questions. We'd also like to hear via the chat what you've liked about the event and the platform or lessons learned that might help others to improve your experience. Kicking off today will be a global team of researchers that has, for the past few months, been helping IBI to develop a methodology which may be used to calculate the sequestration potential of carbonized biomass at the national level. We're calling this the NDC Framework because the underlying objective is to create this framework. In creating this framework is to show national level NDC negotiators or planners the extent to which biochar can be part of helping countries to increase their climate ambitions. Our hope is to have this framework published in a peer-reviewed journal in early 2023 and to raise funding to hire and train a few biochar fellows to help tally these national summaries for a larger number of countries prior to next year's COP. We're often asked what biochar's sequestration potential is globally, and there are numbers being used by the IPCC and others, but we believe it's critical to really determine this at a national level using a standardized methodology, which would then allow us to start rolling up these numbers both regionally and globally. I've been really impressed with how diligent, collaborative, and productive this team has been. each of them brings a deep understanding of a different area needed to develop such a framework. And today you'll hear more about that. Dr. Tom Trabold from the Rochester Institute of Technology, who is both a friend and colleague of mine for many years now, has been spearheading this effort, and he will be moderating and will help with facilitating questions at the end. So Tom, I'm passing it over to you.
Thank you, Kathleen. Hello, everyone. We appreciate the opportunity to present the outcomes of our work today to the IBI Symposium. As soon as the slides are available, I can get started. Okay, great. So before I begin, I'd like to introduce my team of collaborators. From the IBI, we have, in addition to Kathleen herself, Camila Aquije. We also have David LeFebvre from the University of British Columbia, and Fawzy and Ahmed Osman from Trinity Biocarbon. Next slide, please. So to reiterate what Kathleen just stated, the objective of this work was to develop a framework for computing net carbon sequestration potential of biochar that's derived from waste organic resources. And then we, as I'll describe later, applied the framework at a national level to determine biochar's potential in meeting nationally determined carbon or climate targets for two target countries. The methods we used involved acquiring government and literature resources to quantify major sources of organic waste materials. And here we're including materials such as crop residues, forest waste, food waste, paper and cardboard, biosolids, and so on. Then we determine the organic carbon fraction of biochar derived from each of these materials using literature sources and in-house data that the partner collaborators had at their disposal. Then for each country, we assigned a biochar permanence factor, which, as I'll show in a little bit, is a function of only the national average soil temperature. And then lastly, we computed the net avoided greenhouse gas emissions from biochar carbon sequestration, but accounted for the emissions generated over the biochar production and application cycle. And then as an example of the outcomes of the framework, we applied the methodology to case studies for Egypt, which of course was the site of the COP27 meeting, as well as Colombia as representative examples of the framework in action. So next slide, please. So now I'd like to walk you through the major assumptions that were underlying this work. First of all, the framework is based on the generalized approach proposed by the widely cited paper by Wolf et al. And has been applied by a number of researchers since then, including Fawzy, who's part of our team. Second assumption is that we included only waste-derived biomass feedstocks. Therefore, the greenhouse gas emissions associated with the biomass production are not considered in the analysis. However, we do consider emissions from feedstock transport and pretreatment, the pyrolysis plant construction and operational energy, biochar post-treatment and application, and then lastly, loading and truck transport to and from the pyrolysis plant. So we account for both the feedstock, transport and pretreatment, and the biochar post-treatment and transport. The third major assumption is that other greenhouse gas emissions associated with other factors such as biochar priming, nitrous oxide, and methane are not included because these effects are expected to be small relative to the biochar carbon sequestration itself. Next slide, please. The fourth assumption is that the majority of biochar produced will be added to soil. Thus, we're using the permanence factors provided by the Wolf et al. Publication. We do consider the possibility of biochar being used in other long-term industrial applications, such as concrete. However, in these situations, we assume the biochar is shielded from decomposition, so the permanence factor would be equal or greater than that we assign to biochar added to soils. The fifth major assumption is that all biochar is produced under anaerobic conditions at temperatures greater than or equal to 600 degrees centigrade. And at this condition, we're assuming a mean mass yield of 25% on a dry basis for biochar made from most waste feedstocks. The only exception would be in cases where we have empirical yield data for materials that are converted at commercial scale. And in those cases, we use the empirically available number in lieu of the 25% assumption. Next slide, please. Major assumption number 7 is that for conversion conditions of 600 degrees C or greater in a 100-year greenhouse gas inventory period, as was recommended in the Wolf paper, we are using a biochar, or I should say assigning a biochar permanence factor that's a function of only soil temperature. And you can see the curve here for the mean values where the bars represent the uncertainty that was provided in the original paper by Wolf. The 8th major assumption is that we're assigning a single average soil temperature for each country in order to compute the biochar permanence factor. Next slide, please. So based on all those assumptions that I just outlined, we boiled down the framework to this equation. The greenhouse gas emissions or total potential net avoided emissions from biochar carbon sequestration, and here we have units of CO2 equivalent, that is equal to the sum of the products of mass of feedstock times mass yield times organic carbon fraction summed up over all available feedstocks. That sum multiplied by the biochar permanence factor, which, as I said, is a single value based on the country average soil temperature. Then we multiply by 44 over 12, which is the conversion factor from carbon to CO2 equivalent. And then lastly, we subtract the greenhouse gas emissions associated with biochar production and application. So the remainder of the presentation outlines how we went about determining the major variables in this equation: the mass of the feedstocks, for the 2 targeted countries, and then as well as the greenhouse gas emissions associated with the biochar production and application. So at this point, I'd like to invite my collaborator, Fawzy, to outline the methods that he used to quantify the waste biomass resources available in Egypt. Samar, over to you.
Thank you, Tom, and thank you, IBI, for the opportunity to work with this great team to develop this framework. Can we get the next slide, please? So we've been aiming to collect reliable data for Egypt so that we can have meaningful results. As you're aware, collecting data in developing economies is quite challenging. In terms of sources, we looked at published statistics, government statistics, the scientific literature, and obtained consultant recommendations when needed. In our approach, we tried to collect the most recent data. We tried to be as conservative as possible and focused on including major feedstocks. Next slide, please. For feedstock availability, at first we looked at published statistics online, and then we approached the Ministry of Agriculture and Land Reclamation in Egypt for the most up-to-date data, which wasn't actually published yet. We were able to obtain 2020 results covering major crop residues. This was also complemented with published statistics for the organic fraction of MSW, as well as data from the literature for manure and biosolids. In terms of moisture content, this is extremely important as biochar yield is calculated on a dry basis, and this would have had a huge impact on results. So we contacted a specialist to estimate crop residue moisture content for the Egyptian context. The biochar yield was, as Tom said, was assumed at 25% under high temperature pyrolysis. And for some feedstocks with a high or inorganic fraction, we used 30%, which is also a bit conservative. To quantify the organic carbon fraction, we use data from the literature, as well as data obtained through our recent experimental work. Next slide, please. In terms of estimating the mean annual soil temperature in Egypt, we were quite lucky to have found a publication that experimentally measured soil temperature in 6 different cities. The results indicated a range of 18 to 23 degrees Celsius, depending on location. However, to be extremely conservative, we applied a temperature of 25 degrees to compute the permanence factor. Next slide, please. So based on the data collected, these are the results for residue generation, with most data obtained for the year 2020. We have almost 36 million tons of residues on a dry basis generated annually in Egypt. And we believe that this is a conservative number. We didn't include other materials such as like rice husks and bagasse and fruit tree trimmings, as this wasn't included in the data provided by the Ministry of Agriculture. Another approach that could also be deployed for data collection is to use FAO statistics for crop production and identify from the literature the amount of residues generated per ton of crop produced or per hectare cultivated. We'll be looking at this approach to enhance the data for Egypt, as well as for other countries where data availability would be limited. This approach was actually recommended by Axel Renault from Net Zero. Thank you, Axel. Anyway, the results obtained thus far for Egypt are quite interesting, which we'll see later on in the presentation. Now I'd like to invite Camila Aquije to explain the methods used to quantify waste biomass resources in Colombia.
Okay. Thank you, Samer. Hi, everyone. Continuing with the presentation, I researched about the situation in Colombia of 7 themes, like Tom mentioned: organic waste, carbon and paper, crop residues, animal manure, forest waste, biosolids, and construction debris. So, well, first of all, I tried to understand how these themes were evaluated in Colombia, because each country has a different way to present their information. It might be the same entity or ministry, but they have different names to present the information. For example, before we started this research, we were conducting a project to identify all the researchers, users, and our producers in the biochar industry in Latin America and the Caribbean region, so we can collect information on the growth and raw material used in the production process, and also make a database of organic solid waste in each country to determine the availability of this waste. So to have this information, I have to send a lot of emails to the environmental ministries from each country. And I figured out that not all of them had the same information. So you have to communicate with other entities to obtain the data I wanted. So some will have everything you ask for, and they will be okay to share the information with you. But not all countries have information about it, or they will respond anything, and you will have to look through all the reports and documents in the open access website, and they might not be updated. So with that reference in my mind, when I had to look for information of Colombia, it was a little bit easier because you will only need to focus in one country and try to figure out how all the ministries and entities work and which one you should ask for certain data. So after sending in all the emails asking for a specific information, you will have to research by your own so you won't lose time. And if they take a week or a month to respond to you, you will have some backup data. So as you see in the right picture is a response from the Environmental Ministry about biosolids in Colombia. They say they don't have the specific number because not all the cities have a water treatment plant, but they had an estimation of the few plants they have in the country. So sometimes you won't have a clear number, but it's better to have an official number than a wrong one. And the other two pictures are from official entities in Colombia. The first one is DANE. It's the entity responsible for planning, processing, analysis, and dissemination of the official statistics of Colombia. From that website, we obtain information like population, forest, organic residues, carbon, and paper waste. And from the Ministry of Agriculture, they had an official website called Agronet, where they have all the statistics from crop production, number of animals, and other reports. Next slide, please. From that official website called Agronet, we got the top 10 crop residues productions, as you see in the screen. I also review papers to have a solid number for moisture content and also for the residues that come from each crop. For example, in the case of sugarcane, I figured out that 34% is from straw and leaves, and 30% comes from the bagasse, giving us a result of 64% of residues from sugarcane. So at the end of the calculation, we have a total of 46 million tons of residues. Next slide, please. In the case of soil temperature, I found a few papers with formulas to have the final number, but it depended a lot in other variables, so I wasn't very sure about it. But one day, Kathleen shared with us a paper from Torres Eileen from 2022, and she mentioned about the soil temperature in Colombia, and she had a table I saw in other place, and at that moment, it all made sense. I found the map you see in the screen from IGAC, that is an entity in charge of producing the official map and the basic cartography of Colombia. So in that map, you can see the extension of 5 types of thermal floor. The principal is warm, higher than 22 Celsius, and it's the 89.6% of the total area of Colombia. And you see the distribution of the other 4 types of thermal floor in the map as 10.4%. So after analyzing everything, we got an average temperature of 24.2 Celsius. Next slide, please. So in this last table, we have the summary of all the waste biomass sources, which each generation rates, the moisture fraction, and the convertible waste in dry matter. I separated in 2 colors so you can see which information is from the government or official websites. In that case, it's all the crop residues, the forest, the food, the paper and cardboard waste, and also biosolids. And in green, the ones I did my own research from different papers like animal manure and construction debris. So at the end, we had a total of 52 million tons of residues per year of convertible waste in dry matter. So I think I speak really fast, but this is everything I did to obtain the information from Colombia. So right now, I'd like to invite David to explain the methods used to quantify the greenhouse gas emission from biochar production and application.
Okay, thank you very much, Camila. Next slide, please. Okay, so now that we have the methodologies and some of the feedstock quantities, we needed to assess the emissions that are associated with the production and application of biochar. The idea here was to remain very high level and to try to be as conservative as possible. So at the end, what we decided to include was the building materials production for the pyrolysis plant construction, the preheating, size reduction, auxiliary system, and pelletizing energy that's required during the pyrolysis process, the loading operations to load into the truck for transport to and from the pyrolysis plant, and the diesel that's used for biochar spreading once at the field. So next slide, please. Okay, and we tried to combine all of that in the equation that you can see on the screen. So all the parameters here on the left-hand side of the table are what we call fixed factor. So they will not depend on any of the different countries. You see that for some of them, we came up with some distribution, so some uncertainties associated with the data that we found in the literature. So most of the data do come from literature, review, some reports. So yes, next slide, please. But yeah, so there are two parameters here that we decided that we felt were good to be country specific. It's the distance that the truck will have to go through or run between the feedstock, between the pyrolysis plant and the field, and the emission factor associated with the electricity production. Next slide, please. So it's more here. Yes, so for the distance, the combined distance for each country was estimated based on population density. So we kind of streamlined this based on Belgium and a population density of 381 inhabitants per square kilometer, and assign a distance of 100 kilometers, combined distance of 100 kilometers for Belgium. As for the emission factor of electricity, it was taken straight from our world data that combines all the emission factor of electricity of all countries. For the uncertainty assessment, we went for a Monte Carlo simulation with 10,000 iterations. Next slide, please. And this is what the results look like. So each dot on the screen is a country. The whiskers that you see is the results of the uncertainty analysis, and the two green dots represent Colombia and Egypt. So right now, the uncertainty is pretty much the same for each country because we only had uncertainty values for some of the fixed factor, not for the country-specific factor. Next slide, please. So there are indeed a lot of room for improvements there. So we could increase the amount of data that we collected for each processes, extend the uncertainty analysis to all the processes based on the data that we can find, and validate some of the values with some existing life cycle assessment biochar literature. And I would like now to invite Thomas back on screen to finish up the presentation. Thank you very much.
Thank you, David. So if we go to the next slide, we'll walk you through our summary results. And I'll stress at the outset that these are preliminary results because we still have to go back and make sure we have solid references for all of the variables that are going into the calculation. And that's what the team will be working on as we continue completing this work. But I'll walk through each of the case study results in turn. On the left side, we have the results for Egypt. And at the top, I indicate the 2021 population of Egypt, which is 102.1 million. The top table summarizes the organic waste generation rates in millions of tons per year of dry matter. So you can see that in the case of Egypt, by far the largest waste resource is crop residues at 24.7 million tons per year dry. But we also include the organic fraction of municipal solid waste, which was assumed to be 60%, as well as biosolids and animal manure. And the number here, the total is what Samer mentioned before, 35.9 million tons of dry waste available for conversion to biochar. So in the table below, we present the major outcomes of the analysis. So the national average soil temperature, which, as Samer mentioned, was assumed to be 25 degrees. From that value, we compute a biochar permanence factor of 0.76. The computed carbon removal from biochar is 14.8 million tons of CO2 equivalent per year. But from that value, we need to subtract the emissions associated with biochar production and application. So that's based on the analysis that David outlined, 5.0 million tons per year. So our net carbon removal from biochar for Egypt is 9.7 million tons of CO2 equivalent per year. So what we want to do is compare that computed value to the national emissions of Egypt and the per capita emissions, which, as indicated, there are 186.4 million tons per year, and that translates into 1.8 tons per capita. Egypt's NDC target for 2030 is 80.6 million tons of CO2 equivalent. And so, boiling all of these calculations down into the number that we were really interested in arriving at, we see that biochar's potential fraction of the NDC target for Egypt is 12.1%. So on the right-hand side, we go through a similar calculation and presentation of results for Colombia. So Colombia's population is about half of Egypt's, 51.3 million. The organic waste generation rates are split between significant contributions from both crop residues and animal manure, 22 and 22.9 million tons per year dry, respectively. But we also include forest, food, paper waste, and construction debris, which in aggregate contributes 6.6 million tons per year of dry matter. And biosolids also contributes 1.4 million tons per year. So in the case of Colombia, the national average soil temperature, as Camila described, was 24.2 degrees C. From that value, we compute a slightly higher biochar permanence factor than what we used for Egypt, and that was 0.765. Applying the framework equation presented earlier, we come up with a carbon removal from biochar of 25.6 million tons of CO2 equivalent per year, with emissions from biochar production and application of 5.7 million tons per year. So the net carbon removal from biochar in Colombia is 19.9 million tons of CO2 equivalent per year. And in the next two rows, we have the 2020 national and per capita emissions for Colombia. And the NDC target, 2030 target for Colombia is 169.4 million tons CO2 equivalent. So again, computing biochar's potential fraction of the NDC target, we come up with a surprisingly similar number for Colombia, 11.7%. So for both the target countries, Egypt and Colombia, we come up with a potential biochar contribution of about 12% of the nationally determined contribution. I would emphasize, and this was brought up several times throughout the presentation, that we believe these numbers are conservative. Okay, as both Samer and Camila mentioned, there are other waste feedstocks that may be available that were not included in the analysis. So as we continue to refine the model and the acquisition of data, it's quite possible that those numbers may go up slightly. So with that, I'd like to go to the next slide and summarize today's presentation. So our conclusions and future work. Firstly, we've developed a generalized framework to enable quantification of national level greenhouse gas emissions impact of biochar production from waste biomass resources. And we've demonstrated that net carbon removal from biochar may be computed directly from known values of annual waste biomass generation rates, a single value for the national average soil temperature, and assumed values of biochar organic carbon content. And I should also include there the mass yield in cases where we have empirical data and we don't necessarily assume 25% yield. So our future work involves conducting a comprehensive literature review to quantify the ranges of organic carbon content reported for all of these common waste feedstocks. Then we want to quantify the variation in computed net biochar carbon reduction by combining all the uncertainties in the input variables based on the Monte Carlo simulation. Then we intend to provide recommendations for quantifying waste biomass generation rates for countries where limited public data may be available. Both Samer and Camila walked you through their processes for, in many cases, accessing government ministries and online databases to acquire the necessary information. But we want to think about how we would get this kind of data in countries where those resources may not exist. And lastly, our final goal would be to submit a manuscript for journal publication by the first quarter of next year. And then the next slide, I'd just like to show the references that were used. And at this point, I'd like to thank the audience for your participation. And I think we're at the point where we will open up the floor to questions. And I am going to moderate that. So right now I'm going to click on the question and answer button. And let me see if I can look through these quickly and so let's see. So someone asked, could you explain the methodology to obtain carbon removal factor and the biochar's potential fraction of NDC? Yeah, so the methodology was laid out in early in the presentation, where we demonstrated that a generalized framework could be generated by considering three main factors: the mass generation rate of the waste feedstocks, an assumed yield, and an assumed organic carbon fraction. From that product, summed over all of the available waste feedstocks, we could come up with a total carbon removal potential of biochar. From that value, we have to subtract any emissions that were generated in biochar production and application. So that's how we came up with the removal factor, if you will, for the biochar. Those numbers were then compared to the nationally determined contributions for the two countries, and that was just based on published data from the IPCC on NDC commitments that countries made at the Paris meeting, I believe in 2021, or no, I'm sorry, in 2015 Paris meeting. Those NDC commitments were made. So I hope that answered your question. If not, we can discuss it further in the rooms later, the networking room later this afternoon. So another question is, how were animals' manure taken into account? There are many different sources and methods with different factors, like to produce biofertilizers or biogas. So I think for that, I would invite Camila to respond, because I know she did a lot of work on that in Colombia.
Yes. Well, it was a tricky question because with Tom, we spoke about this in many reunions because I didn't know how to collect that information. The first thing I did was try to understand how the animals work in the farms and that's things, and see how many time they were outside, how much time were inside, how much hours they sleep, and it was a lot of estimations made. But I found a paper from Colombia where they did kind of the same, but in a better, with better formulas, and everything was right. And they estimate the animal manure, and we took that number as a reference for animal manure in Colombia. Yes.
Okay, great. Thank you, Camila. And again, if there's interest in further discussion, please join the networking room later this afternoon. The next question, which I would direct to David, is I'm wondering why the biochar production emissions relative to total biochar production is much higher for Egypt compared with Colombia.
Yeah, okay. So relative to, sorry, I'm trying to find the question because I forgot it. Yeah, relative to total biochar production, I do not have an answer for that. What I can tell you, though, is that the emission associated per ton of biochar produced of Egypt were around 504 kilograms CO2 equivalent per ton of biochar produced. And for Colombia, it was around 433. And this is mainly due to population density and also emission factor of electricity. It's only due to that. And this is really, again, I cannot say much more than that. Yeah. I guess the carbon content of the different biomass that were taken into account for each country must play a role. So yeah, the type of biomass.
Okay, great. Thank you, David. So another question, why do the greenhouse gas emissions only include biochar mass? Why not also include fossil fuels avoided by using syngas, product gas that's produced from the biochar production? Of course, only if that said gas is used for some end purpose which avoids fossil fuel burning. So this is a very relevant question. And I think this speaks to the technology that's used to produce the biochar, of course, and that's an important factor. We're assuming here that the technology used is designed to favor biochar production. So some of the systems that we're familiar with, and in fact, one that I use quite regularly, which is a small commercial scale system, really only has two co-products, the biochar itself and then waste heat. because the syngas is combusted to provide energy for drying the biomass itself. Okay, so in the case of this, again, the system I'm familiar with, which is representative also of other systems that are on the market, really only has a fairly small amount of excess waste heat available that could be used to, say, displace natural gas use. But again, we're assuming that the system is designed to favor biochar production. So we did not include waste heat utilization or syngas utilization. But this also gets back to the point that was made early on, that we believe these estimations we're making are conservative. Of course, if we're actually able to use some of those other co-products, the greenhouse gas benefit would be even greater than the numbers that we're presenting here. Okay. Again, if you'd like to have further discussion on that, happy to do so later on in the networking session. Let me see, just looking through some of the other questions. Another question is, how do you ensure that forest waste wood is really waste, excluding over extraction of dead wood and impoverished, and I'm not exactly sure of the term here, xylophagous fauna, that is deadwood eating bugs? So would maybe Samer, I know that you're currently working with tree residues, and could you comment on, how do you determine that forest waste or wood waste is really waste, and we're not overlooking other potential benefits of that material?
Well, to be honest, Tom, coming from Egypt, we have very limited forest resources here. So I mainly work with tree trimmings, but these are from agricultural activities. So like olive tree trimmings or citrus tree trimmings. And they have to do the pruning annually or biannually anyway, to as part of their cultivation practices. But to be honest with you, I'm not really familiar with the forestation activities.
Okay, that's fine. Thank you. I guess the main point is that we certainly have to be cognizant of other potential uses of what we're perceiving as waste materials. Those factors were definitely not considered in our calculations, but that is an important point that we'll make sure that we address in our final publication, because we don't want, I just to reiterate what was said earlier, the calculations are believed to be conservative, but we want to make sure that we're not missing things as this participant brought up about unknown benefits that could be eliminated if we're using that material as a waste feedstock for producing biochar. Another point, I guess this is more of a comment than a question, but I think it's an important one. The participant stated that the greenhouse gas emissions from producing biochar from crop waste should be offset by emissions from burning crop waste. That is, the top-down burn method of making biochar from crop waste greatly reduces emissions from burning. So again, that's a very interesting point. That is not something we considered in the analysis. Again, if we included that in the analysis, it would make the numbers, the biochar contribution, look even bigger. So again, in the spirit of being conservative, we did not include that. But it is an interesting point. And I wonder if, again, I can ask Samer or Camila to comment on that. In your analyses conducted in your target countries, did you encounter any information about waste feedstocks that are currently burned, and that by making biochar, we would be offsetting the emissions associated with that burning?
Well, I read in a few papers that they kind of do that in the areas, but I don't have like a final answer for that.
Okay.
Yeah, Tom, do you mind me making a comment about this question?
Oh yeah, please.
Okay, so it's a very good point, and indeed it would increase the overall greenhouse gas capture potential of the practice. But I think there's another question that kind of resonates with that one, and it had to do about potential energy production out of for pyrolysis or other uses for biomass. And I think, like from an LCA perspective, we really try to remain conservative, and this means also not taking into account other potential uses for the biomass, at least, well, yeah, use that could have happened. Because if we start doing that, then we start entering the consequential world of life cycle assessment, and this can lead to thousands and thousands of different scenarios, and everything gets tricky from there. So I think that the choice that we made of not taking advantage of the avoided emissions from burning biomass, staying on the conservative side, allow us also to prevent us from going to the consequential world of LCA, which dramatically increased the potential number of scenarios. I hope that answers the question.
Great, thank you, David. Another question that I think is relevant. I'll ask Samer to comment on this. The participant asked, does the methodology consider the fact that the investigated residues may have other uses? Is the competition part of the assessment? And Samer, I just wanted to ask you to comment, because I know in your work, and in many of our earlier discussions, you did mention that many of the waste feedstocks in Egypt already have a productive use, right? So that is something that we have to take into account.
Well, definitely there's competition for biomass. Certain residues like wheat straw, rice husks, go into animal feed formulas, and they're quite expensive. But again, this is from a business perspective. But for the purpose of what we were trying to do, we just accounted for 100% of the residues within the framework. But yeah, we in reality there's competition. It's reflected in prices, and it kind of dictates what we can use, what we can't use, and there's also other aspects in terms of residues with trace metals, and sometimes that cannot be used for agricultural applications. Which we assume that all the actual biochar is going back into the soil. So again, we tried to simplify the framework as much as possible. We accounted for 100% of these residues being converted into biochar and going back to the soil.
Okay, great. Thank you, Samer. This next question I would direct to David, because it's related to how we accounted for biochar production. If the syngas is burnt after pyrolysis, how are the generated greenhouse gas emissions accounted for in the carbon sequestration procedure?
Yeah, so that's a great question again. So what we assumed the pyrolysis technology to be would be like a medium to high tech kind of technologies, and also an autothermal one, where the syngas are actually burned inside the machine itself to heat up the entering biomass. So right now in this analysis, there is no energy that is accounted for the pyrolysis machine itself, and there is no emissions that is associated with the pyrolysis process as well. meaning that, yes, we assume it would be medium to high technology, and so there would be limitation in terms of emissions from the pyrolysis, and also that most of the energy produced through pyrolysis would be used to actually run the machine. Yeah, I hope that answers the question.
Okay. Thank you. Thank you, David. This next question I would direct to Camila, because it's related to the quantification of the waste feedstocks. And the participant asked, have you assumed 100% of the crop and forest residue could be collected and used for biochar, or allowed for retention in some residues, for example, mulch? And have you also considered inefficiencies in collection?
Yes, sorry, I was like reading again. Yes, yeah, for that, we try to understand how the crops or the crops work, because not all of the residues was 100% like residues. No, in the case of avocado, for example, with Tom, we were talking about like the residues from avocado could be like the peel and the seed. So we said like the seed is a residue or it's not a residue, because they use it to generate or produce another plant. So it's gonna depend on the crop that we talk about. But I kind of try to consider that in all the crop production or we analyze. So yeah, I don't know if I responded everything.
Mm-hmm.
But yeah, that will be my answer. In the case of forest residue, I had the response from DANE, from the entity from Colombia, and they have like a really good, like separated the subproducts from the wood. So they have a really good system in that case of how much wood they have from the forest waste.
Thanks, Camila. Yeah, I guess I would just add that this question is really very important, because we often overlook the logistics associated with collecting and pre-processing the feedstock. In actuality, that's often the most difficult step in the entire process, right? The pyrolysis itself, which we all kind of focus on, that's sort of the easy stuff. It's figuring out how to collect and pre-process and transport all of the waste materials. That's often the most challenging part of the whole process. So I think this question is really important, and we do have to pay attention to things like collection efficiency. Just because, let's say, 100,000 tons of something is produced per year, that doesn't mean that you can actually secure 100,000 tons of material to convert into biochar. So very important point there, and I appreciate that question. Okay, with that, we are out of time. This session is completed. Thank you all for your participation. We appreciate the opportunity to present the results of our research, and I would ask you now to please switch over and close out of this session and log into the next session. And again, we're happy to talk to you further in the networking session this afternoon. Thank you.